Assalamu alaikum. This is Pushpita Khan, ID 200021354, presenting my slides on rectangular waveguides of microwave engineering. So let's get started. In the beginning, let us first understand what a waveguide is. Waveguides are crucial for carrying electromagnetic waves at microwave and millimeter wave frequencies, and the rectangular waveguide is one of the most common types due to its simplicity and efficiency. In this presentation, I will explain what a rectangular waveguide is, how it works, the modes inside it, cutoff frequency, field patterns, applications, and some important parameters that we must consider while studying waveguides. So, what is a rectangular waveguide? A rectangular waveguide is a hollow metallic tube with a rectangular cross-section. It guides electromagnetic waves from one point to another with minimal energy loss. And unlike cables, where signals travel through conductors, in waveguides the energy is confined within the hollow space by reflecting off the walls. So, why do you think we use waveguides? Uh, at the high frequencies, traditional cables like coaxial cables suffer from significant energy loss due to radiation and dielectric heating. Waveguides solve this problem by ensuring that most of the energy stays inside using reflections on the walls, making them highly efficient for microwaves, radar, satellite communication, and more. There are a few important dimensions that we need to work with uh, in rectangular waveguide microwave engineering, such as the width, which is denoted by A, and the height, which is denoted by B. These two are very important dimensions of a rectangular waveguide. The A is also known as the larger side of the rectangle, and the B is known as the smaller side of the rectangle. Typically, the width is greater than the height, so A is greater than B, and these dimensions determine the operating frequencies and the type of wave modes the waveguide can support. Now, let us discuss the modes that are used in rectangular waveguides. A rectangular waveguide usually supports different types of electromagnetic wave modes, such as the TE modes or the transverse electric modes. Mm, this is like an electric field that is transverse to the direction of propagation, and as the name suggests, it is known as the transverse electric mode. And the other one is TM mode, which is also called the transverse magnetic mode. And again, as the name suggests, the magnetic field is transverse to the direction of propagation, and thus it is known as transverse magnetic mode. And in a rectangular waveguide, uh, transverse electric mode is usually dominant because it requires the lowest cutoff frequency. So, what a cutoff frequency is? A waveguide does not support all frequencies. This is a very important thing that we need to keep in mind while working with waveguide because below a certain frequency called the cutoff frequency, no waveguide can propagate. The cutoff frequency, FC, or transverse electric modes is given by the formula that you can see on the screen. It is half root over m divided by a whole square plus n divided by a whole square, uh, and the entire thing will be multiplied by c, where m and n are the mode numbers, a and b are dimensions, and c is the speed of light. The TE mode, for TE mode, the cutoff frequency FC is calculated by dividing dividing C with 2A. This is why selecting the correct dimension A is crucial in a waveguide design. Next up, field patterns. Inside the waveguide, the electromagnetic fields form patterns. For TE mode, the electric field varies sinusoidally sinusoidally across the width, and the magnetic field forms circular loops. These field patterns help in the efficient transfer of microwave engineering. Next, propagation constant and phase velocity. The behavior of waves inside the guide is characterized by propagation constant beta and phase velocity Vp. And beta can be calculated by root over k square minus kc square, where k is the number of waves and kc is the number of cutoff waves. And Vp can be calculated by dividing omega by beta. Here, k, or the free space wave number, is 2 pi by lambda, and kc is cutoff wave number. And interestingly, inside a waveguide, phase velocity is greater than the speed of light, but the actual energy, which is group velocity, moves slower. Then comes attenuation. Although waveguides are efficient, they still have some attenuation, such as conduction losses and dielectric losses. So what is conduction loss? Conduction loss happens due to imperfect conductivity of the metal walls, and dielectric losses happen when the waveguide is filled with a material instead of air. Attenuation is lower at higher frequencies, but it also increases if the frequency is too high and beyond the waveguide's design. Let's talk about some practical applications of rectangular waveguide. It's useful for radar systems, it's useful for satellite communication, it's used in microwave links, and last but not the least, it is very useful for laboratory testing equipments. Their ability to carry high frequency signals with low loss and minimal interference makes them essential in modern communication and defense systems. So, for wrapping up, we can say that rectangular waveguides are efficiently uh, very useful and a wonderful form of engineering for carrying microwave signals. The TE mode is the most dominant mode of all. The cutoff frequency of microwave engineering in the rectangular waveguide depends on the waveguide's dimension, and field patterns inside the guide help in understanding energy distribution. Waveguides are a pillar of modern microwave systems, offering low loss and reliable transmission for high frequency signals. Thank you so much for listening. In waveguides, a transverse electric or a TE mode is characterized by having no electric field component in the direction of wave propagation, which also means that the electric field is perpendicular to the direction the wave is traveling. To have a visual representation of what I just explained, let us see this animation, which I have taken from YouTube to have a better understanding on this topic. So as you can see, the wave is propagating forwards, and at the same time, the electric field is perpendicular to the direction of the wave propagation. That's why it's called transverse electric wave.